I welcome you all in the fifth lecture on camps and followers. In the fourth lecture, we talked about the first type of the follower motion, in which the follower was supposed to be moving with the uniform or constant velocity. And we also discussed in detail about the displacement, velocity and acceleration imparted to the follower. In this lecture, we will talk about the second type of the motion which would be imparted to the follower. So in this particular case, the follower is supposed to be moving with uniform acceleration and retardation during its rise and fall. Figure shows the displacement curve of a follower which moves during its outward stroke with uniform linear acceleration and deceleration. It performs half the outstroke with uniform acceleration and the remaining half with uniform retardation, or a portion with uniform acceleration and the remaining with uniform retardation. On the return stroke also, it may fall by half the return stroke with uniform acceleration and the remaining half with uniform retardation, or a portion with uniform acceleration and the remaining with uniform retardation. Displacement is found to be parabolic in this case. Magnitude of the acceleration and the deceleration is the same and constant in two halves. Now we shall carry out a mathematical analysis of displacement, velocity and acceleration and jerk for a follower which is moving with uniform acceleration and retardation during its rise and return. So let us first get familiar with the nomenclature. Theta naught and theta r, these are the angular displacement of the cam during its outstroke and the return stroke of the follower, and that we measure in radians. Omega is the angular velocity of the cam in radians per second, and usually this angular velocity of the cam is constant. T naught is equal to theta naught by omega, and this is nothing but the time required for the outstroke of the follower in seconds. Likewise, Tr is the time required for the return stroke of the follower in seconds. V naught is the maximum velocity of the follower during its outstroke, and Vr is the maximum velocity of the follower during its return stroke. F naught is the uniform acceleration of the follower on the outstroke, and Fr is the uniform acceleration of the follower on return stroke. Now, for a follower which is moving with uniform acceleration and retardation during its rise and return, the expression for the displacement is given by the second law of motion, s equal to ut plus half ft square. Here, that is the initial velocity of the follower is 0, so the general displacement s is equal to half of ft square. Now, the displacement of the follower at any instant can be represented as y. So y is going to be equal to half f, and t is replaced by theta upon omega square. Since the angular velocity of the cam is usually constant, and in this particular case the acceleration of the follower is already a constant term, because the follower is supposed to be moving with uniform acceleration and retardation. So in this particular equation, what we are keeping fixed, f is fixed, then omega is also fixed. So y is going to be that is equal to k times theta square, where k is nothing but f upon 2 omega square. So this f upon 2 omega square, these are the constant parameter. So y can be written down as k times theta square. So this is going to be the equation number 1. So this is nothing but the equation for the displacement of the follower. So when we differentiate this particular equation number 1 with respect to time, what we get is the velocity. So velocity is going to be v equal to dy by dt. So differentiating the equation number 1 with respect to time, we get twice k theta into d theta by dt. D theta by dt is nothing but angular velocity of the cam again. So it can further be written as twice k omega into theta. This is my equation number 2. So equation number 2 is basically for the velocity of the follower. Upon double differentiation, that is second differentiation of the equation number 1, we will get the acceleration. So acceleration denoted by f is equal to d2y upon dt square. So upon finding out the second derivative of this with respect to time, what we get is it is twice omega k dt by dt. So the equation for the acceleration imparted to the follower is going to be twice k omega square. This is my equation number 3. So thus for constant value of angular velocity of the cam, the acceleration is constant. Obviously here, as long as omega is constant, k is already a constant, 2 is a mathematical digit which is a constant, so acceleration is going to be a constant term. So here we again cross verify it, that the acceleration of the follower is coming out to be a constant term. So these equations are valid for the first half of the rise. First half of the rise means when the cam turns through an angle of half of the outer stroke angle. That is, theta is equal to theta 0 by 2. So now we can check the values given by equation number 1, 2 and 3 at theta equal to 0, means when the cam just starts rotating and follower is at the bottommost position. So y is going to be 0 because there is no displacement imparted to the follower when the cam just begins to rotate. At theta equal to theta naught by 2 means when the cam has turned through an angle of half of the outstroke angle. So what we notice is when we insert theta equal to theta 0 by 2 in the equation, first what we get is we get y equal to s by 2, where s is the total lift imparted to the follower, or it is nothing but equal to the stroke of the follower. So obviously at theta equal to theta 0 by 2, when the cam has turned through an angle of half of the outstroke angle, the follower is definitely at its half of the total lift. So y is going to be s by 2. So from here we notice that s by 2. So we just insert these value y equal to s by 2 over here in this equation number 1 and theta equal to theta 0 by 2. So what we get is we get the value of the constant k as 2s upon theta 0 square. Now substituting the value of constant determined earlier by equation number 3 back into the equation number 1, that is the displacement of the follower, what we get is 2s theta 0 square into theta. And the velocity it becomes 4 omega s into theta divided by theta 0 square. So now what we can do, we can just cross check the value of the velocity when it is maximum. So V maximum is determined as inserting theta equal to theta 0 by 2. So what we get is the maximum velocity of the follower is at the, that is half of the outstroke angle. So it is going to be twice s upon theta 0 into omega. Likewise, we determine the value of the acceleration. Acceleration is going to be 4 omega square s upon theta 0 square. So what we get is f equal to 4 times s upon theta 0 square into omega square. So with the help of these 7 equations, we can always determine the displacement of the follower till it reaches half of its stroke, and likewise we can determine its maximum velocity or acceleration. Now we focus on the, that is, movement of the follower for the second half of its rise. So the equation for the displacement of the follower for its rise during the second half, it is given by y equal to s minus k theta 0 minus theta square. So let us just check it, the equation number 8, whether it is correct or not. So at theta equal to theta 0 by 2, we know that the displacement of the follower is half of its total stroke length, or half of the total lift imparted. So inserting this y equal to s by 2 here on the left hand side, s is written as it is. Value of the k, we already know it. The value of the k is twice s upon theta 0 square. So twice s upon theta 0 square, and theta 0 is as it is, and theta is going to be theta 0 by 2, square of that. So finally what we get is the equation comes out to be s by 2 is balanced by the right hand side equal to s by 2. It means the continuity of the displacement curve is verified using this equation number 8. Now we can differentiate this equation number 8 with respect to time in order to determine the velocity of the follower for its movement during the second half of the rise. So velocity is determined by differentiating this expression, equation number 8. So what we get is, we get expression for the velocity given by equation number 9 as twice k theta 0 minus theta into omega. Again we can determine the value at theta equal to theta 0 by 2 when the follower is at the half of its stroke. So velocity is going to be determined as k theta 0 into omega. If we insert the value of k given by twice s upon theta 0 square, so again we get the same value which is equal to the Vmax. So it is also the same as Vmax at theta 0 by 2 from the earlier expression given by the equation number 6. So with the help of this, the first half of the rise and thus verifies the continuity of the velocity curve. The acceleration in the second half of the rise is given by f equal to, so what we do for determining the acceleration during the second half of the rise, we just differentiate the velocity expression with respect to time again. So dv upon dt will give me the acceleration of the follower during its second half of the rise. So that is given by the equation number 10, minus 4 omega square into s divided by theta 0 square. So with the help of the equation number 10, what we notice is that the acceleration is constant of the same magnitude but opposite to the acceleration in the first half of the rise, because there was a negative sign in that. Since there is a sudden jump of acceleration to a finite value of 4 omega square into s upon theta 0 square at theta equal to 0, at theta equal to theta 0 by 2 and theta equal to theta naught. The jerk is infinite at all these points, that is p is equal to infinity at theta equal to 0, theta equal to theta 0 by 2 and theta equal to theta naught. In order to determine the jerk, what we can do is we can further differentiate the expression of acceleration with respect to time and determine the value of the jerk by inserting theta equal to 0, theta equal to theta 0 by 2 and theta equal to theta naught. So ultimately what we get is the value of the p comes out to be infinity at all these 3 points. So let us now summarize what we have derived right till now. The maximum velocity of the follower during the outstroke is given by expression twice omega s upon theta 0. Then maximum velocity of the follower during the return stroke is given by twice omega s upon theta r, where theta naught is the outstroke angle and theta r is the return stroke angle. Maximum acceleration of the follower during the outstroke is given by 4 omega square into s divided by theta naught square. Likewise, we have maximum acceleration of the follower during the return stroke given by 4 omega square into s divided by theta r square. Having determined all the values for displacement, for velocity, maximum velocity, acceleration and jerk, what we can do is we can have a graphical representation of all these 4 parameters as shown in figure 1. So figure 1 basically shows a graph for the displacement, velocity, acceleration and jerk during the outstroke. So here we are assuming that the cam undergoes a rotation equal to its outstroke angle. So along this abscissa or x-axis, what we are having a cam angle measured in radians, and its value is equal to theta naught. So for the outstroke angle rotated by the cam, we are going to plot the variation of the displacement, variation of velocity, acceleration and jerk. So if we plot the displacement imparted to the follower for the outstroke rotation of the cam, ultimately what we are going to get is we move along this path, and at the end of this outstroke the follower is at its peak. So the total lift imparted to the follower is equal to s. So definitely when the cam undergoes a rotation, suppose the cam has undergone the total outstroke angle is say 90 degree. So when the cam has turned through an angle of say 10 degree, the lift imparted to the follower is this much. When the cam has undergone a rotation by 20 degree, this much is the lift imparted to the follower. When the cam has undergone a rotation by say 50 degree, this much is the lift imparted to the follower. So if we just move through this path, ultimately this shows the displacement curve for the follower when it is supposed to be moving with uniform acceleration and retardation. Now we know that the follower is moving with uniform acceleration and retardation. So obviously for the movement of the follower up to its half of the outstroke, so up to its half of the outstroke, the follower moves with uniform acceleration. So ultimately the slope of this velocity profile that is the velocity versus the time. Ultimately what we have done here is, instead of taking the time along abscissa, we have taken the cam rotation angle theta, because that is angular velocity of the cam is constant and omega is nothing but d theta by dt. So ultimately when omega is constant, so time can be represented in terms of the cam rotation angle theta. So this velocity contour is going to be a straight line. So ultimately it's a straight line having a positive slope. It reflects that the follower is getting accelerated up to half of its rise, means that when the cam turns through an angle of theta 0 by 2 up to half of its stroke, the follower moves with uniform acceleration. Then it acquires the maximum velocity at this particular point, and then it starts reducing, means the uniform retardation is observed by the follower. So its velocity continues to reduce in equal time interval by equal amount. During this uniform acceleration, the velocity of the follower increases by equal amount in equal time interval. So ultimately, when we focus on the acceleration contour for this particular follower, which is supposed to be moving with uniform acceleration, obviously, all of a sudden the follower attains a certain velocity, and there is no time taken by the follower for that attaining the velocity. So the acceleration has got a finite value over here. Then it remains with it moves with constant acceleration during half of its lift up to this particular point. Then it acquires the maximum velocity, and thereafter the velocity continues to decrease. So all of a sudden the acceleration changes its sign. It becomes a retardation case now. So there is a deceleration of the follower. So again, this deceleration is again constant. So its velocity continues to decrease by equal amount in equal time interval. So acceleration is again here a constant. But when we look at the jerk, at theta equal to 0, there is infinite amount of the jerk produced, because all of a sudden the follower gets accelerated within no time interval, within 0 time frame. It automatically gets accelerated to this value. So it basically imposes infinite amount of jerk at theta equal to 0. Then at theta equal to theta naught by 2, all of a sudden the uniform acceleration gets converted into uniform retardation. So it basically again changes the sign, and the time taken by this change is 0. So ultimately again there is a jerk in the negative direction. It is infinite jerk is there. When the follower is now at its peak, cam has undergone a rotation equal to the outstroke angle. Again the acceleration is basically getting its value equal to 0. So again there is a infinite amount of jerk produced here. In this particular figure, what we have done here is we have plotted the displacement, velocity, acceleration and jerk contours for one complete rotation of the cam, that is from 0 to 360 degree of its own rotation. So we observe that from 20 degree to 160 degree, the follower is basically getting lifted up with uniform acceleration up to its half of the outer stroke, and remaining half is covered by the follower by uniform retardation. Then from 160 degree to 200 degree, the follower observes a first dwell period of 40 degree, and there is no movement of the follower. It is now at this particular location, the follower is having its maximum lifted position, and it remains at that position for 40 degree rotation of the cam. So this is the first dwell period. So the movement of the follower is 0 here, so velocity of the follower becomes 0 during this time interval. From 200 to 340 degree of cam rotation, the follower again returns back. So again, this first half of the return is with uniform acceleration, and the remaining half of the return is with uniform retardation. Then beyond 340 degree to 360 degree, that is by 20 degree this much and 20 degree at this particular point. So 40 degrees again the dwell period observed by the follower. So you can see here that the velocity is 0 during this 20 degree rotation of the cam, and for this initial 20 degree rotation of the cam, the velocity of the follower is again 0. So we observe that the velocity contour for this type of follower, which is supposed to be moving with uniform acceleration. So this velocity versus time plot is a straight line, so it basically represents that the velocity of the follower increases by equal amount in equal time interval. It becomes maximum when the follower is at its half of the that is outstroke, that is half of its lift. It acquires the maximum velocity, and thereafter again the velocity starts decreasing by equal amount in equal time interval. Then at the end of this, when the cam has turned through an angle equal to the outstroke angle, the velocity of the follower becomes zero. Now it observes a dwell period, so its velocity remains zero. Now the follower beyond this particular point has started coming down. So this is basically the return of the follower. Again, it is basically having a uniform acceleration because its velocity again increases by equal amount in equal time interval. So it is basically a case of the that is a uniform acceleration. Again, at the half of its return stroke, it acquires the maximum velocity, and then it observes a retardation, and again followed by a dwell period, second dwell period. So when we look at the acceleration plot at this particular point, all of a sudden the follower acquires a certain velocity. So the acceleration has got a finite value. It jumps from a zero value to a finite value within no time frame, and thereafter it remains constant. So ultimately the follower is getting accelerated uniformly. Then as soon as the follower is at its half of its lift position, total lift imparted, then it changes its sign. Earlier it was getting accelerated, now it is getting decelerated. Then again it becomes zero because this is the dwell period, there is no velocity imparted, so there has to be no acceleration here. Again, during this return period, this is shown by a negative sign of the acceleration. So this is basically the uniform acceleration. Then it changes the sign and it is becoming a uniform retardation now. So we observe that at this particular point, the acceleration jumps from a value of 0 to a finite value within no time interval. So delta t is basically 0 here. So that's why it produces infinite jerk at theta equal to, that is, say, so this is basically the moment from where the follower gets lifted up. So we will call it as theta equal to 0 degree. So when theta is 0, when the cam has just started rotating and follower is basically getting lifted up, the infinite jerk is produced. When the follower is at half of its total lift position, it is again observing a infinite jerk. When the follower is has completely been lifted up, it is again observing a infinite jerk. So same is the condition for the return of the follower also. So from it can be observed from the plots shown in figure 1 that there are abrupt changes in the acceleration at the beginning, midway, and the end of the follower motion. At midway, an infinite jerk is produced. Thus, this program of the follower is adopted only up to moderate speeds. Now there are certain points that you guys should remember for motion of the follower with uniform acceleration and retardation. Constant acceleration motion during a rise or fall sequence produces the smallest possible values of acceleration for a given rise and time interval. The displacement diagram for a rise or fall interval is divided into two halves, one of constant acceleration and the other of constant deceleration. The shapes of each half of the displacement diagram are mirror image parabolas. This motion scheme, also known as parabolic or gravity motion, has constant positive and negative accelerations. It has an abrupt change of acceleration at the end of the motion and at the transition point between the acceleration and deceleration halves. These abrupt changes result in abrupt changes in inertial forces, which typically cause undesirable vibrations. Therefore, this motion in its pure form is uncommon except for low speed applications. A scaled displacement diagram is required to construct the actual cam profile. The equations derived can be used in conjunction with a spreadsheet or other equation plotting package to complete this diagram. Although this analytical method is precise, care must be taken to plot the diagram to scale. Graphical construction of a displacement diagram is an alternative method to generating a displacement diagram to scale. Such a construction using the constant acceleration motion scheme can be accomplished by referring to figure 1 and using the following procedure. So following procedure is basically adopted to plot the displacement curve of a follower moving with uniform acceleration and retardation during outstroke. First point is divide the follower rise or fall sequence into two halves. AE represents the time period and EF represents the magnitude of rise for the first half of this motion scheme. Then divide both the horizontal and vertical axis of the quadrant AEFH into equal parts. Then construct the vertical lines from the horizontal divisions. Then construct the straight lines from corner A to the vertical divisions. Draw a smooth curve through the points of intersection of the vertical lines and the lines drawn from corner A. Repeat steps 2 through 5 for the remaining half of the curve as shown in quadrant FICG in figure 1. A constant acceleration fall is constructed as a mirror image of figure 1. So what we have done here is along this abscissa what we have taken is we have taken the outstroke angle of the cam, that is theta naught. So ultimately for constant angular velocity of the cam, theta naught is nothing but directly proportional to time. So whether we are plotting the time along the x-axis or plotting the cam rotation angle along the x-axis, it does not make any difference. So suppose the outstroke angle of the cam is say 80 degree. So what we have done here is along the abscissa we have taken the outstroke angle of the cam, and for 80 degree outstroke angle value what we have done is we have assumed some scale. For the sake of understanding, we can assume that every centimeter taken along the x-axis represents 10 degree rotation of the cam during its outstroke rotation. So what we have got here is because the total angle we assumed for the outstroke rotation is 80 degree. Every centimeter represents 10 degree rotation of the cam, so it's going to be 10, 20, 30, 40, 50, 60, 70 and 80. So what we have done, we have plotted here a line having 8 centimeter length and we have marked the graduations here. So what we are going to do is we are going to divide this line AB into 8 number of equal parts. So that is even number of parts, this line has to be divided into that is n number of even parts. So we have divided this line into 8 number of parts. Then we know that how much is the lift of the follower, that is by what amount the follower gets lifted up. So what we have done here is we have taken along this ordinate or the y-axis the rise imparted to the follower. So first we focus on that is A, E, F and H. So what we have done, we have basically divided this 8 centimeter line into 8 equal segments and we have marked them as point 1, 2, 3, E and so on. Then what we are going to do, we are going to divide this rectangular box which is made up by this, that is the cam rotation angle taken along the x-axis and the lift imparted to the follower taken along the y-axis. So what we are going to do is we will look at the central ordinate. Central ordinate means this is the first ordinate, this is second, this is third and this one is the fourth ordinate. So this is going to be my central ordinate. So I will also divide this central ordinate into same number of parts as I divided the abscissa. I divided the abscissa in 8 number of parts. So I am going to divide the central ordinate into the same number of segments. So 1, 2, 3, 4, 5, 6, 7 and 8. So these are going to be the division of this central ordinate. Now what we will do, we will first focus on that is the uniform acceleration case. We know that the follower rises up to its half of the stroke, up to the half of the stroke with uniform acceleration. So we are going to focus on A, E, F and H, this particular quadrant only. So from this leftmost bottommost corner we mark it as point number A. Now we start joining the point A with point number 1, point A with point number 2, point A with point number 3 and point A with point number F. Then these dotted lines are getting intersected with these ordinates drawn from point number 1, drawn from point number 2, drawn from point number 3. So the intersection of the line A1 with the first ordinate is marked here, this particular location. Then intersection of the line A2 with the second ordinate is here. Intercept of the line A3 with the third ordinate is here, and the intercept of the line AF with the fourth or the central ordinate is at the point F itself. So we just mark these intercepts here, 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 and at point number F, and we join all these points by means of a smooth curve. So this is going to be the displacement curve for the follower during its first half of the outstroke. Then we focus on the second quadrant, that is movement of the follower for rise during its rise for the next half. So what we are going to do here is in the similar way we have chosen this point C. We have also divided this line into four number of parts, 1, 2, 3, 4. Then we start joining the point number C with the first segment here, then C with the second, C with the third, and C with the central ordinate. And we focus on the that is the intercept of this first line with the first ordinate, second line with the second ordinate, third line with the third ordinate. So we identify these intercepts and just join them by means of a smooth curve. So that is ultimately how we get the displacement of the follower when the cam turns through an angle of outstroke angle theta naught, and the total lift imparted to the follower is S, and this is the displacement of the follower for its first half of the total outstroke, and this is for the remaining half of the total outstroke. This is a slightly more enlarged view of the displacement curve of a follower moving with uniform acceleration and retardation during the outstroke. So what we have done here is the total outstroke angle of the cam is theta naught. So theta naught has been taken along the abscissa, and we have divided this total outstroke angle into n number of even parts. So we have divided this outstroke angle into 8 number of parts. So this is basically a even number. So we have taken the equal parts, so we name them as 1, 2, 3, 4, 5, 6, 7, and 8. And from all these points we draw ordinates. We draw the vertical lines. So along this abscissa or along this y-axis, we have taken the height of this rectangle equal to the lift or the total stroke of the follower. Then we focus on the central ordinate of this particular rectangular box. So central ordinate is also divided into 8 number of even parts, 8 number of equal parts. So 1, 2, 3, 4, 5, 6, 7, and 8. Then we start joining the first segment taken on the central ordinate with the leftmost bottom corner of this rectangular box. So this is the first line. The intercept of this first line with the first ordinate is marked here as this particular location. Then we join this left corner with the second intercept, and then this line is getting intercepted with the second ordinate here. So we just mark this point here. Then the line which is obtained by joining the left corner with the point number 3 is also having its intersection with this third ordinate at this location, and likewise with the central ordinate at this particular location. So we join all these intercepted points by means of a smooth curve. So this is nothing but the displacement imparted to the follower during its first half of the outstroke. Then the similar procedure is adopted for the remaining half of the outstroke. So what we do here is we had earlier divided this central ordinate into equal number of even parts. So this is first part, this is second, third, and fourth. Now we start joining these points, that is point number 8, 5, 6, 7, 8, 8, 7, 6, and 5, and 4 from this rightmost top corner of this rectangular box. So this is the first one, and its intersection with the first ordinate is here. Intersection of the second line with the second ordinate is here. Intersection of the third line with the third ordinate is here, and intersection of this diagonal of this rectangular box with the central ordinate is at point number 4. So these intercepted points are again joined by means of a smooth curve, so which basically gives us the displacement of the follower during its later half of the outstroke movement. So here we notice the displacement curve of a follower moving with uniform acceleration and retardation during outstroke, dwells and return stroke. That is for one complete rotation of the cam. So theta naught is the outstroke angle turned through by the cam. Then there is a dwell period in between, and then there is a return stroke, and return stroke is further followed by another dwell period. So this is the total angular displacement of the follower for one complete rotation. So we observe that the outstroke angle starts from here and it ends at this particular point. So as we already explained earlier, we are going to divide this angular, that is outstroke angle line taken along the axis into n number of equal parts. So we have divided it into 8 number of parts. We have drawn ordinates from these points 1, 2, 3, 4, 5, 6, 7 and 8. Now we focus on the central ordinate. We divide the central ordinate also into 8 number of equal parts. So these parts are A, B, C, D, E, F, G and H. Then we start joining this leftmost bottom corner of this rectangle, that is point number A, with point number small a, point number A with B, A with C, A with D, and we look at the intercept made by this line A small a with the first ordinate. This is my point number B. Then the intercept of the line AB with the second ordinate it is at point number C. Then the intercept of the line AC with the third ordinate, it is at point number D. So likewise we keep on getting these points, and we join them by means of a smooth curve, which is shown here by this pink line. So this is nothing but the displacement imparted to the follower during the outstroke angle. So follower at the end of this outstroke, now the follower is at this particular location. Now it has got its maximum lift. Now we observe that this blue line, this pink line, it is going to be horizontal one. So there is no change. So follower remains lifted up here. So there is no movement imparted to the follower during this duration. So this is nothing but the first dwell period observed by the follower. Then after this, the cam undergoes further rotation, and it basically turns through an angle which is equal to the return stroke angle. So during its return stroke, we again follow the same procedure. We divide this return stroke angle of the cam into n number of equal parts, that is even number of equal parts. So we have further divided them into 8 parts, and naming them as 1 dash, 2 dash, 3 dash, 4 dash up to 8 dash. And we draw ordinates from all these points, and then start joining the central ordinate, the points marked on the central ordinate with the left top corner of this particular outstroke angle box. So we follow the same procedure. This particular left top corner is joined with 7 dash point, and its intercept on the first line is taken. Then the line which is obtained by this corner with the 6 dash, its intercept on the second ordinate is chosen. Likewise on the third ordinate, likewise on the central ordinate, and we continue to get this line, that is the pink color line, and this is nothing but the return of the follower during the return stroke angle of the cam. And then there is no lift imparted to the follower, so this is going to observe a second dwell period.